to our next speaker, who is Björn Globisch. I hope that I said the surname good enough. Who is head of the Terahertz sensor system group at the Fraunhofer Heinrich Hertz Institute. And he's going to talk us about optoelectronic terahertz solution for industrial sensing and spectroscopy. So now you should be having the role of presenter soon, I think, and you should be able to share with us your presentation.
All right. Do you see my screen now?
Yeah, perfect. I see the PowerPoint or the PDF. Yep.
Okay. And you can see my cursor as well, I hope.
As well. Yeah, we see it.
Excellent.
Thanks very much.
Then, Alex, thank you very much for the introduction. As already said, I'm going to talk about optoelectronic terahertz solutions for mainly industrial sensing in this talk and a little bit about spectroscopy. So thank you very much for inviting me to this webinar. And before I start, I would quickly like to introduce the Fraunhofer Gesellschaft, so Fraunhofer Society. It is Germany's largest society for applied research, and in total we have 68 institutes that are located in Germany and all around the world. And basically these institutes cover the full range of science, starting from medicine to engineering, from social science to law, basically. So everything is more or less covered. And in total, it's 26,000 people working there, mainly scientists and engineers. And the budget is quite high, with 2.5 billion euros. And HHI is part of this Fraunhofer Society since 2003. And the idea of Fraunhofer is to do applied science. So covering more or less the gap, or bridging the gap between universities and industrial applications. And the typical revenue structure that is given by our headquarters is listed here. So we are more or less forced or pushed towards directly cooperate with industry. And of course, we have research projects that are funded by national, European, and international funds. And then we get very little basic funding from the federal government. So the message here is that we aim to do applied research. And this is why I'm going to talk about industrial applications of terahertz in this talk, because this is what we aim to do. So the Fraunhofer Heinrich Hertz, which is located in the center of Berlin, here we see the nice skyscraper building, which is ours. We have a bit more than 300 employees, something like 200 students, and this third-party funding and the industry contracts are quite high. And the unique thing that we have in our institute is that we have a full semiconductor process line based on indium phosphide that we can use for our technology. I'm going to talk about this in a second, that we use basically a semiconductor to generate and to detect terahertz. And the backbone for doing this is this indium phosphide process line that we have here, where we can fabricate nice semiconductor structures that we offer in the foundry service and multi-project places as well. So that's more or less the basic introduction of the institute. Now I would like to talk about what we do in terahertz. So we exploit, or we use, this indium phosphide semiconductor technology for making terahertz emitters and receivers, for pulse systems, so for time domain spectroscopy, and also for continuous wave terahertz systems. And we start, as you can see here with this small picture, we start from the bare wafer, from the bare substrate. Then we make our emitters and receivers. We package them into these sensor heads that you can see here. So that's more or less a plug and play device that you can use for generating and detecting terahertz. And then we still go one step further and make fully integrated systems that you can use to drive these sensors. So in the end, you have a spectrometer, and this spectrometer you can use for non-destructive testing, for spectroscopy, and also for imaging. And in principle, we have two different technologies in the Institute, as I already said. One is the time domain thing, so the pulse terahertz. One is the frequency domain. And here are some key facts about these systems. So first of all, the time domain thing covers a quite high bandwidth, starting from something like 100 gigahertz to 6 terahertz. The measurement rate is with 100 traces per second, it's quite okay for industrial process control, and the frequency resolution is quite high. So this technology would be best for thickness measurements of thin dielectric layers. And this is what I'm going to talk about mainly in this talk. Then we also have a frequency domain platform with a little bit lower bandwidth, actually a higher update rate, much higher frequency resolution. And this technology, which is behind it, is essentially more simple than the pulse technology. But the pulse technology is already, let's say, industry ready, whereas this continuous wave technology, we are starting to push it into that direction. And I'm sure that the next speaker, who is Guillermo Carpintero, he will talk a lot about this frequency domain applications. And this is why I'm going to focus my talk on the pulse application, which is shown on the top of the slide. So what's the general idea of captured pulse system, which is also called Terahertz TDS, Terahertz time domain spectroscopy? So the idea is quite simple. Here on the left-hand side of this slide, you see a time trace and also the frequency of an optical infrared pulse with a very short time duration. So the pulse duration is 80 femtoseconds, a very short optical pulse. The interesting thing is that generating these short pulses is more or less easy. So you have industrial lasers that are used and that can generate these short optical pulses, and the bandwidth of these pulses is very, very high. So they cover a bandwidth of more than 10 terahertz. So in the optical domain, it's very easy to generate a broad spectrum covering more than 10 terahertz. And the idea now is to use this optical engine to generate an electrical signal that you can see here on the left, on the right-hand side of the slide. So what you want to end up with is something like this time signal and a spectrum that covers frequencies from 100 gigahertz to at best 10 terahertz. And the idea of how to do that is to use a very fast switch that is illuminated by the femtosecond pulse and that translates this optical femtosecond pulse into the electrical domain. And this is what we focused on the last 10 years in developing and improving these semiconductor substrates that can be used for generating and detecting terahertz radiation. So in principle, what you need for a pulse terahertz system is just a femtosecond laser, an emitter and a receiver, and an optical delay line, which creates a time delay between the terahertz and the optics in order to raster scan the electric field of the terahertz. And the idea of what we wanted to do is to make it industrial grade, compact, easy to use, and cost efficient. So we wanted to use very small femtosecond lasers, which are already commercially available, so you can buy them. We wanted to make these fiber coupled emitters and receivers that you can directly plug to the laser and use it, and then make these compact systems that I already talked about that are allow for quite high measurement rates and that are turnkey and can be put in an industrial production line. And this is what we did over the last year. So we mainly focused on improving the signal that we generated. So this is in 2012. When I started with Terahertz, we were more or less here. And over the last 7 to 8 years, we improved it so that we now really cover a really broad spectrum with quite high signal-to-noise ratio. So we have 6.5 terahertz and a quite high signal-to-noise of more than 100 dB. And this is now the backbone that we use to address applications. And now let's come to the application. This actually is the application I would like to talk about mostly in this presentation. And this is an article that was published in 2015, stating with the headline "Car paint measurements in industrial killer applications for terahertz." So we are still working on searching for the real industrial killer applications for terahertz. And in 2015, it was stated, okay, maybe it's car paint measurements. And the reason for that is the following. So car paint consists of a multi-layer of different dielectrics. So here is a small sketch. So you have a substrate, and on top of the substrate, you have different layers. One is the primer, then you have the color code, and then you have a clear coat. And all these layers can be penetrated with terahertz radiation. So that's the first thing that's good about it. Then terahertz is a contact-free measurement. So you can directly, after applying the paint to the car, you can directly measure the thickness of the layers. Then you can get micrometer resolution with terahertz because the wavelength is in this range. And then you can measure multiple layers at the same time. And you can measure coatings on metal and plastic. So it doesn't matter if it's a metal car or if it's a plastic car, plastic part of the car, so something like the bumper. So this is why it was thought, okay, terahertz might be the best way of fulfilling this measurement task. And actually, it turned out that it's really a very good choice. And up to now, it's the only technology that can fulfill all these 4 points that are listed on the right-hand side of the slide. And what you see here in the inset is a typical pulse trace of such a terahertz measurement, where you can see partial reflections. So these peaks here correspond to the interfaces of the different layers. And you can, in this case, nicely distinguish them by the eye. When the layers become thinner and thinner, it's getting more and more complicated. But this is the actual idea. And over the last 5 years, we worked quite hard with our partners to get a system up and running that can be used in a car manufacturing paint line. So what we did is we wanted to make a fully automated terahertz sensor system for industrial non-contact thickness measurement. So everything starts, of course, with the box that I already showed. So with the time domain spectrometer. So we have this with quite high speed, with quite high bandwidth. This is what we integrated now into a rather complicated control system. So everything starts here with a material database where you have the terahertz properties of all the different paint layers that you want to use. Then you have a robot that is used to measure different points of the car with terahertz radiation. So you have an external control for this robot cell. Then you feed this into a gateway, and then you have here a rather complicated control unit that is there to synchronize the actual terahertz measurement and the robot movement in order to link these 2 points with each other. In addition, what you also need is in a real industrial factory, you have vibrations, and this vibration restores your signal. So our partners, mainly this company Fisher, who have more than 50 years experience in layer thickness measurement, they implemented such a vibration compensation. So in real time, we compensate for the vibration of the car body in order to get accurate measurement results. Then you have this terahertz spectrometer, which is connected, which is shown here. And then in the end, you have the head that is used for the measurement and reflection geometry. And this also has a quite unique feature, which is the dry air purge, which you need for getting really accurate results of thin layers in order to get rid of water vapor absorption. And then we have a 3D scanner that actually scans the position of the sensor head with respect to the car body in order to get fast and reliable positioning of the sensor. So in the end, we have a fully integrated system that can be put in a car manufacturing line, and this is what we are actually doing. We have a demo system which is now installed at different OEMs for paint layer thickness measurement. So let's quickly talk about the measurement results that we get with this system. So here again, we see a small sketch of a typical car paint on a metallic substrate. So we have the substrate. We have, first of all, a primer, which mainly covers all the surface roughness of the metal substrate. Then you have a base coat, and then you have a clear coat. And when you now look at the terahertz signal, which is now a processed signal, after going through all these algorithms and the transfer matrix model that we use for it, you get these nice results here. So you can clearly distinguish the primer from the substrate. You get the interface of the base coat and the primer. You get the clear coat and the base coat, and then you get the interface between air and clear coat. So you can nicely distinguish between all these layers. And from the time difference between these layers, you can calculate the thickness. And as I said, you can not only do this for a metal substrate, which is shown here on the left-hand side, this also works for a plastic substrate. The main difference is just the shape of the signal. Here for the metal, with a very high refractive index, you get the signal upside, and from the plastic with a comparably low refractive index, this signal is turned. So in the end, you can use it for metal and plastics. And what we get with this system is we can measure up to 5 layers with individual signals between 5 and 200 microns. The accuracy of this is better than 500 nanometers, actually. And the relative standard deviation of consecutive measurements is more than 1%. So we have a quite accurate and reproducible measurement system. And the next thing that we are actually quite...
Sorry, Javier, sorry to interrupt. It would be good if you could more or less finish in about a couple of minutes, 1-2 minutes.
Yeah, I need 1 or 2 more minutes. It's quite fast. So one thing which is quite annoying still about terahertz measurements in reflection geometry is that we still use discrete emitters and receivers, and that makes reflection measurements quite hard because either you have an angled terahertz beam path or you need a beam splitter. And we're currently working on an integrated transceiver, so a single module that looks orthogonal to the sample surface without any beam splitters. And this is what we have been developing for 5 years now. And the main idea is just putting emitter and receiver on the same semiconductor chip. So here you see the receiver, there you see the emitter. And then you can use it as a real compact reflection head. And we did that over the last years, and very recently, so 2 days ago, a paper about our latest result on this transceiver appeared, where we made a direct comparison between this rather bulky reflection head that you see here and the compact terahertz transceiver that you see here. And here is the result of the comparison. So you get with the separated one in blue and the transceiver one in green, you get more or less the same result. And to our opinion, this is one of the crucial things to get terahertz technology to even more applications in sensing. And with this, I would like to summarize my talk. So I hope I could show you that we have a terahertz TDS system, which is all fiber coupled, covers a large bandwidth, and has a really high dynamic that can be really nicely used for non-contact layer thickness measurements. And I showed you an application of car paint thickness measurements with up to 5 layers. And we get minimal thicknesses of 5 microns with an accuracy better than 500 nanometers. And for the Outlook, we are working on the monolithical terahertz transceiver, a real compact reflection head. And we are also working on a fully automated lab system for thickness measurement that you can see here. And it's not connected to a robot that can be put on a lab table. And with that, I would like to thank you for your attention, and I'm happy to answer your questions.
Thanks very much, Björn, for your talk. It's amazing the combination of lasers that you've achieved to generate these terahertz solutions. So I see that there are a couple of questions. Well, there are quite a few questions, so I think we have time for a couple of them. I will read them in order of they leave them here. So Elena Martinez asked us if how different can be the coatings to be able to be distinguished as different layers. Is it possible to know the composition as well?
Yeah, so this measurement scheme is mainly, it measures the difference in refractive index of the coating. So if you have really similar coatings, it's getting harder and harder to distinguish them. So what we need is a difference of approximately 0.1, 0.05 in the refractive index in order to distinguish the coating.
Okay, and is it possible to know the composition?
Yeah, you should know the composition beforehand.
Okay.
It's extremely important. So if you want to measure really thin layers, you have to know the composition beforehand.
Okay. I see. And we have some more questions. And the next one I see here is if it's possible to accurately measure the thickness of the superficial oxide layer of ferrous scrap materials with huge heterogeneity in shape stock in big piles. Maybe that's a very specific question.
That's true. So oxide layers are typically very, very thin, right? So they are typically thinner than 5 microns. And these 5 microns are actually the resolution limit of the system.
I see. Yeah, I see. Then you are right at the limit for this sort of applications. I see there are a couple of more questions, but unfortunately we are running a bit short on time. So if you can leave your email here, maybe they can directly address them to you.
Excellent. Okay.
Great. So thank you very much, Björn, again for your talk.